Imagine crossing a wide, sunlit field thousands of years ago. Dust rises beneath your feet as scattered reddish-brown stones lie across the ground. Sunlight catches their rough surfaces, but they don't glitter or shine. They feel heavier than expected, yet seem ordinary in every other way. Farmers step over them. Builders wedge them into simple walls. Children kick them aside without a second thought. To everyone, they are just rocks. But hidden inside those dull, rust-colored stones is a material that would one day transform human civilization. It would shape tools and weapons. Later, it would build machines, bridges, railways, and the steel skeleton of modern cities. For thousands of years, humanity lived beside this remarkable resource without recognizing its value. That is what makes iron so fascinating. The real mystery is not simply how people learned to use it. It's how anyone discovered that ordinary-looking stone concealed something so extraordinary. Iron ore gives away almost nothing. It doesn't glitter like gold. It doesn't shine like native copper. It looks like weathered earth. Yet, through generations of observation, failed experiments, and patient trial and error, early metalworkers uncovered one of history's greatest technological breakthroughs. But iron's story does not begin underground. It begins in the sky. Long before humans learned to extract iron from rock, they encountered it in a far more dramatic form. It fell from space. In ancient Egypt, meteoritic iron was associated with the heavens and crafted into precious objects for royalty. In Mesopotamia, similar celestial iron was treated as something rare and extraordinary, often linked to divine origins. To these civilizations, it was more than metal. It was a gift from the sky. But if the first iron came from the heavens, an even greater mystery remains. How did humans learn to recreate on Earth what had once fallen only from space? Imagine standing in an ancient desert after a brilliant fireball streaks across the night sky. Hours later, people discover an unfamiliar object buried in the ground. It is unlike any stone they have ever touched. It feels unexpectedly heavy. When struck, it dents instead of shattering. Freshly exposed surfaces glimmer with a metallic shine. Unlike ordinary rocks, it seems almost alive with strange properties. To ancient people, there was only one explanation. It had fallen from the heavens. Long before anyone learned to produce iron from ore, meteorites gave humanity its first encounter with naturally occurring metallic iron. These fragments formed inside ancient asteroids and traveled through space for millions of years before reaching Earth. Because they already contained iron naturally alloyed with nickel, they could be shaped without the difficult process of extracting metal from rock. Cultures across the ancient world recognized that these celestial stones were different. Egyptian texts described iron as metal from heaven, reflecting the belief that it came from beyond the earth. Similar ideas appeared in Mesopotamia, where celestial iron was treated as a rare and extraordinary material. Modern archaeology supports these ancient beliefs. Iron beads from pre-dynastic Egyptian burials contain unusually high levels of nickel, a clear signature of meteoritic iron. Centuries later, the famous dagger buried with Pharaoh Tutankhamun was also shown to have an extraterrestrial origin. These were not ordinary tools. They were prestige objects, symbols of wealth, power, and divine connection. During the Bronze Age, iron could even be valued more highly than gold in certain contexts. People admired it, collected it. In some cultures, it was regarded as a sacred material, but they still couldn't create it. Meteorites proved that iron existed. They revealed nothing about how to make it. That answer remained hidden inside ordinary red stone, waiting for humanity to unlock one of history's greatest technological secrets. Imagine standing beside a Bronze Age furnace. The fire roars. Bellows force air into the glowing chamber. Inside, copper-rich stones slowly surrender, releasing molten metal exactly as ancient metalworkers expected. Then a different stone is added, a reddish piece of iron ore. They wait. Nothing useful happens. The rock darkens and glows in the heat, but it refuses to behave like copper. When the fire finally dies, it remains almost unchanged, a heavy, stubborn piece of earth. To early metalworkers, the conclusion seemed obvious. This wasn't metal. It was just rock. That misunderstanding delayed one of humanity's greatest discoveries. Unlike gold or the occasional lump of native copper, iron almost never appears in metallic form. Over immense stretches of time, it reacts with oxygen, becoming iron oxide, the reddish material we know as iron ore. Ancient people weren't looking at hidden metal. They were looking at rust locked inside stone. The challenge wasn't finding iron. It was learning how to reverse that natural chemical process and separate the metal from oxygen. Bronze Age furnaces were designed for copper and tin, which could be worked at much lower temperatures. Iron demanded something very different. Extracting it required hotter furnaces and the right chemical conditions, something early technology could not reliably achieve. Generation after generation, the result was the same. Failure. People knew iron existed. Meteorites had already proved that. But turning ordinary rock into usable metal remained impossible. The obstacle wasn't human intelligence, it was the limits of fire itself. Iron wasn't hiding from humanity. It was waiting for a new kind of furnace, one powerful enough to unlock a metal trapped inside stone since the beginning of the Earth. The breakthrough didn't happen because someone suddenly became a better scientist. It happened because generations of craftspeople slowly built better fires. At first, ancient furnaces were little more than open hearths. They worked well enough for cooking food and firing pottery, but most of their heat escaped into the air. Over time, that began to change. Metalworkers discovered that charcoal burned much hotter than ordinary wood. With less moisture and fewer impurities, it produced a cleaner, more intense fire. Then came another improvement. Instead of leaving flames exposed, they surrounded them with walls of clay and stone. These enclosed furnaces trapped heat, while tall shafts created a natural draft that pulled fresh air through the burning charcoal. The fire grew hotter. Then came the greatest advance: bellows. By forcing a steady stream of air into the base of the furnace, bellows supplied oxygen faster than nature alone ever could. The charcoal burned more fiercely, temperatures climbed, and furnaces moved closer to the conditions needed for iron production. Many of these improvements were originally developed for pottery, copper, and bronze production rather than specifically for iron. Iron became the unexpected beneficiary. Without realizing it, generations of craftspeople had been solving a hidden puzzle. Their furnaces were finally becoming capable of unlocking the chemical process that separated iron from oxygen. And when that invisible reaction finally succeeded, it produced something no one expected: not a pool of molten metal, but a rough, black, spongy mass that hardly looked valuable at all. When ancient metalworkers broke open that strange black mass, they discovered the first usable iron ever made from ordinary stone, and history would never be the same. When the furnace was finally broken open, no glowing river of iron appeared. Instead, metalworkers pulled out a rough, black, sponge-like mass mixed with ash and glassy waste. At first glance, it barely looked like metal at all. This strange material is what we now call a bloom. It formed because the iron never actually melted. Instead, oxygen had been removed from the ore, leaving behind countless tiny particles of metallic iron tangled together with trapped slag. The bloom was only a beginning, not a finished product. In its raw state, it was almost useless. The real transformation happened next. While still glowing hot, the bloom was placed on a heavy anvil and struck repeatedly, again and again and again. Each hammer blow forced molten slag from its porous structure. Every strike compressed the iron, gradually forge welding the tiny metallic particles into a stronger, more solid mass. Slowly, the bloom became denser, stronger, workable. But this demanded remarkable skill. A blacksmith couldn't strike at random. The temperature, timing, and rhythm of every blow determined whether the iron became a reliable tool or cracked beneath the hammer. Generation after generation, metalworkers perfected this craft without understanding the chemistry inside the metal. They didn't need to. Experience taught them what science would explain thousands of years later. By the end of the process, the shapeless bloom had become wrought iron, a material tougher, more flexible, and far more useful than anything that came directly from the furnace. Still, one important weakness remained. Wrought iron could bend without snapping, but it struggled to keep a sharp edge. The final step toward true steel would come from an unexpected change inside the fire itself, one discovered almost entirely by accident. For a time, wrought iron seemed like the answer. It was durable. It could be reshaped again and again. It resisted breaking far better than stone. But blacksmiths soon noticed one frustrating weakness. After repeated use, iron blades slowly bent and lost their sharp edge. Bronze, despite its limitations, could sometimes stay sharper for longer. Then something unexpected began happening inside the forge. Some iron tools emerged noticeably harder than others. No one knew why. Ancient blacksmiths had never heard of carbon atoms or crystal structures, but they were careful observers. Over generations, they noticed that iron left in close contact with burning charcoal for long periods behaved differently. It became tougher. It held a sharper edge. It performed better in the hands of soldiers, farmers, and craftsmen. The answer had been hidden inside the fire all along. At high temperatures, tiny carbon atoms from the burning charcoal slowly entered the surface of the iron. This gradual process enriched the metal, changing its internal structure without changing its appearance. Then came another discovery. If this carbon-rich iron was cooled rapidly, often by plunging it into water, it became even harder. To the blacksmith, it must have seemed almost magical. The same piece of iron emerged from the forge stronger than before. Without realizing it, Generations of craftsmen had uncovered one of metallurgy's greatest breakthroughs, steel. No single inventor claimed the discovery. The knowledge spread through experience, apprenticeship, and countless hours beside glowing furnaces. One better blade, one stronger chisel. One small improvement after another, until iron was no longer competing with bronze. It was beginning to surpass it. Yet bronze did not disappear overnight. For centuries, the two metals existed side by side, and only the collapse of great civilizations would finally open the way for iron to reshape the ancient world. If steel was the superior material, why didn't ancient societies immediately abandon bronze? The answer wasn't technology, it was economics. For nearly 2,000 years, bronze had been the foundation of civilization. Kingdoms relied on it for weapons, farming tools, and construction. But bronze depended on two different metals. Copper was relatively common. Tin was not. Ancient civilizations depended on vast trade networks to obtain it. Those routes crossed mountains, deserts, and seas, connecting distant cultures through the exchange of a single essential resource. For centuries, the system worked. Then, around 1200 BCE, much of the eastern Mediterranean entered a period of widespread upheaval. Powerful kingdoms weakened. Major cities were destroyed or abandoned. Long-distance trade networks collapsed. Historians still debate the exact causes: climate shifts, invasions, internal conflict, earthquakes, or several disasters occurring together. But one consequence is clear. Reliable access to tin became increasingly uncertain. Civilizations faced a difficult choice: wait for a metal that might never arrive, or use the one beneath their own soil. Iron ore was abundant. Unlike bronze, it did not depend on distant trade. Communities with access to ore, charcoal, and skilled blacksmiths could produce their own metal. Ironworking itself was not new, but necessity accelerated its wider adoption. Techniques improved. Furnaces became more efficient. Blacksmiths refined their craft. Generation by generation, iron replaced bronze across much of the ancient world. The Iron Age did not begin because iron suddenly appeared. It began because an old economic system collapsed, and a more abundant material was ready to take its place. Once iron became practical, it spread with remarkable speed. Its greatest advantage wasn't simply strength, it was accessibility, allowing ordinary communities to shape powerful tools from the rock beneath their own land. One of iron's greatest strengths had nothing to do with hardness. It was availability. Unlike bronze, iron did not depend on rare shipments traveling across distant trade routes. Its raw material was far more widely available than the tin required to make bronze. A village didn't need wealthy trading partners or access to distant mines. It needed iron ore, charcoal, a furnace, and someone who understood the craft. That changed everything. As ironworking spread, metal gradually became less exclusive. Over time, tools once limited to elites became increasingly accessible to ordinary communities. Farmers gained stronger plows and axes. Carpenters worked with tougher chisels. Blacksmiths forged nails, hinges, knives, and countless everyday tools that quietly transformed daily life. The impact reached far beyond warfare. Iron axes made clearing forests more practical. Iron plows opened heavier soils that earlier tools struggled to break. With better tools, communities cultivated more land, harvested more food, and supported growing populations. The metal beneath their feet was steadily reshaping entire economies. Yet to the people living through it, the process still seemed mysterious. A blacksmith could take an ordinary stone, feed it into a roaring furnace, hammer a dark, glowing mass while sparks filled the air, and finally reveal a sharp blade or sturdy tool. Without any knowledge of chemistry or physics, the transformation looked almost supernatural. Across many cultures, blacksmiths earned deep respect. Their knowledge passed from master to apprentice through practice rather than books. To outsiders, it looked less like craftsmanship and more like magic. That sense of mystery followed iron wherever it spread. Yet different societies solved the challenges of ironworking in remarkably different ways, and those discoveries would shape the future of metallurgy for centuries to come. As ironworking spread across the ancient world, one surprising pattern emerged. There was no single path to mastering the metal. Different civilizations faced the same challenge, yet solved it in remarkably different ways. In China, furnace technology advanced beyond the traditional bloomery. Their furnaces reached much higher temperatures. For the first time, iron became fully molten, allowing the production of cast iron. Although brittle compared with wrought iron, cast iron could be poured into molds, making it ideal for producing large numbers of agricultural tools and other practical objects. In India, metalworkers followed a different path. Instead of casting iron, they perfected methods for producing exceptionally high-quality steel. By carefully heating iron inside sealed containers, they created steel of remarkable strength and durability. Centuries later, this material became the source for many of the legendary blades associated with Damascus steel. Elsewhere in parts of Africa, ironworkers designed furnaces suited to their local environments. Some relied on tall natural draft furnaces that generated powerful airflow without constant mechanical bellows, What makes these developments remarkable is that many of them emerged independently. The people behind them shared no modern chemistry, no universal textbook, no global scientific network. Yet through observation, experimentation, and generations of practical experience, they reached many of the same discoveries. Iron was no longer the achievement of one kingdom. It had become a technology shaped by countless cultures, and its greatest influence was still ahead. Once stronger tools became widely available, they began transforming not only workshops but entire civilizations. The next revolution would not happen inside the furnace. It would unfold across fields, forests, and growing cities, where ordinary iron tools quietly reshaped everyday life on a scale the ancient world had never seen. The true revolution of iron wasn't fought on battlefields. It happened in farms, forests, and workshops. Imagine a farmer standing before a field of dense, heavy soil. With wooden or bronze-tipped tools, breaking that ground demanded enormous effort. In many regions, large areas remained difficult to cultivate efficiently. Iron changed that. Stronger iron plows cut deeper into the earth, opening soil that had resisted cultivation for generations. More land could be farmed. Harvests gradually increased, and growing communities gained more reliable food supplies. The same transformation spread beyond agriculture. Iron axes made clearing forests faster and more practical. Iron saws and chisels gave carpenters greater precision. Blacksmiths forged nails, hinges, chains, and countless everyday tools. Together, these small inventions strengthened buildings, wagons, and the equipment people relied on every day. Few of these tools became legendary. Most were ordinary, yet together they quietly transformed civilization. Iron's greatest contribution was never a single famous weapon. It was the thousands of practical tools that made ordinary people more productive. A stronger plow could feed more families. A better axe could clear new farmland. A durable chisel could help build stronger homes. One improvement supported another until entire societies became more efficient than ever before. Iron had become more than a metal. It had become infrastructure, a silent partner in nearly every trade that sustained civilization. And it all began with one remarkable discovery, that an ordinary-looking rock concealed extraordinary potential. Yet iron's story was far from over. New furnaces, better forging techniques, and bold engineering ideas would soon push this ancient metal into an entirely new age, laying the foundations of the modern world. For thousands of years, iron production depended on muscle and endurance. Blacksmiths pumped bellows by hand. Workers swung heavy hammers. Every tool demanded hours of skilled labor beside a blazing forge. Then everything changed. The Industrial Revolution didn't replace iron. It multiplied its potential. Water-powered and later steam-powered machinery transformed iron production, allowing furnaces and forges to operate on a scale earlier generations could scarcely imagine. Inventors also developed more efficient methods for refining iron, making production faster, cheaper, and more consistent than ever before. The result was not simply more iron. It was an entirely different world. Railway tracks stretched across continents. Steam engines carried people and goods farther than ever before. Factories filled with iron and steel machines produced tools, textiles, and equipment at unprecedented speed. Cities transformed. Bridges crossed rivers that had once divided communities. Iron frameworks supported larger buildings than ever before. The metal once believed to have fallen from the heavens was now shaping nearly every part of modern life. Yet the most remarkable part of the story was its continuity. The blast furnace replaced the ancient bloomer. Steam hammers replaced handheld tools. But the goal remained unchanged. Release iron from stone, shape it with heat, improve it through skill. The scale had changed beyond recognition. The principle had not. Even today's steel mills still follow the same essential journey that began thousands of years ago beside a charcoal furnace. Yet one remarkable truth remains. Every bridge, skyscraper, railway, and machine still depends on the same element that ancient people once mistook for an ordinary reddish stone lying quietly beneath their feet. Perhaps the most astonishing part of iron's story is how ordinary it appears. Walk across almost any landscape, and you are likely standing above iron-bearing rock. It lies beneath hills, inside mountains, scattered through soils, and exposed along riverbanks. Iron is one of the most abundant elements in Earth's crust, yet much of it remains locked inside minerals, hidden in plain sight. But abundance alone never changes history. Knowledge does. For countless generations, people lived beside iron ore without understanding what it contained. They saw the reddish stone. They picked it up. They built with it, yet they could not unlock the metal hidden inside. Only after centuries of experimentation did humanity discover the right combination. Charcoal, controlled airflow, carefully designed furnaces, and the patient skill of forging. Step by step, those discoveries transformed ordinary rock into one of civilization's greatest resources. That lesson reaches far beyond metallurgy. History is filled with materials that existed long before people recognized their true value. Iron simply became one of the greatest examples. The resource itself was never rare. The knowledge required to use it was. As that knowledge spread from one generation to the next, the landscape itself seemed to change. The same hills that once looked ordinary became sources of opportunity. Entire industries grew around deposits that earlier societies had ignored. In the end, the discovery of iron was never about finding something new. It was about learning to see what had always been there. And that change in understanding helped reshape human history. The greatest legacy of iron isn't hidden in ancient furnaces or forgotten blacksmith shops. It surrounds us today in the bridges, buildings, railways, and machines that still depend on the same remarkable discovery first made thousands of years ago. Look around you for a moment. The building you're sitting in, the bridge carrying traffic across a river, the railway stretching toward the horizon, even the vehicle parked outside. Chances are every one of them depends on iron. We often think of steel as an entirely different material. In reality, steel is simply iron combined with carefully controlled amounts of carbon and, in many cases, other alloying elements. The modern world is still built upon the same element that ancient blacksmiths struggled to free from ordinary rock. Only the methods have changed. Today's blast furnaces, electric arc furnaces, and advanced rolling mills produce millions of tons of iron and steel with remarkable precision. Engineers design different grades of steel for different jobs. Some are lighter, others are stronger, more corrosion resistant, or built to withstand extreme environments. Yet beneath all this technology lies a familiar story. Iron ore is still mined from the earth. Oxygen is still removed from the ore. Heat still performs the essential work. And skilled people continue shaping the metal into forms that support modern civilization. The scale is vastly different from an ancient bloomery. The underlying principles remain remarkably similar. That continuity connects today's engineers with generations of metalworkers who refine their craft through centuries of observation, experimentation, and experience. Every skyscraper, every railway, every wind turbine, every cargo ship, each carries a small part of that shared history. The modern world may seem unimaginably distant from an ancient forge, but without those early discoveries, many of the technologies we now take for granted would never have existed. Yet the greatest part of iron's story isn't only what humanity built with it. It's how patience, curiosity, and thousands of years of experimentation transformed an ordinary stone into one of the foundations of civilization. Looking back across this entire journey, one realization stands out. The greatest discovery wasn't iron itself. Iron had always been here. It formed inside ancient stars long before Earth existed. It became part of the material that formed our planet billions of years ago. Locked inside rocks, mountains, and minerals, it remained hidden while countless generations walked across it without understanding what lay beneath their feet. What truly changed history was human curiosity. Someone noticed that certain stones behaved differently in a fire. Someone experimented with charcoal instead of ordinary wood. Someone built a slightly taller furnace. Someone discovered that greater airflow produced more heat. Another person learned that repeated hammering created stronger metal. None of these breakthroughs transformed civilization on their own, but together they formed a chain of knowledge stretching across centuries. Each generation inherited what the previous one had learned, then added something new. That slow accumulation of experience eventually unlocked iron's potential. This pattern appears throughout history. Progress rarely arrives in one dramatic moment. More often, it grows through thousands of small observations, countless failed experiments, and the determination to keep asking better questions. Iron is one of history's clearest examples of that process. An ordinary reddish stone became the foundation of civilizations not because nature changed, but because human understanding did. Perhaps that is why this story still matters today. It reminds us that the world's greatest discoveries are not always hidden in distant places. Sometimes they have been quietly surrounding us all along, waiting for someone to look a little more closely. And that brings us to the final chapter. Because the true legacy of iron isn't measured only by the tools, bridges, and cities it created, it's measured by what its remarkable journey reveals about humanity itself. When we think about history's greatest inventions, we usually picture the finished product: a sword, a bridge, a locomotive, a skyscraper. But iron tells a different story. Its greatest achievement was never the objects it became. It was the journey that made those objects possible. Think back to everything this story has revealed. A mysterious metal falling from the sky, ordinary rocks hiding extraordinary potential, generations of failed experiments beside smoky furnaces, the accidental discovery of steel, the rise and fall of civilizations, the spread of knowledge across continents. None of these moments changed the world on their own. Together, they did. Iron reminds us that progress is rarely driven by a single brilliant idea. Instead, it grows through patience, observation, experimentation, and the willingness to pass knowledge from one generation to the next. Every blacksmith who improved a furnace, every craftsperson who refined a forging technique, every apprentice who learned from a master, each added another piece to a puzzle that no single person could ever complete. The Iron Age was not created by one civilization. It was built by countless people in different places. Across thousands of years, they solved similar problems, shared what they learned, and gradually unlocked the full potential of iron. Their discoveries transformed not only a metal, but the course of human history. In many ways, iron became a symbol of something greater than metallurgy. It became proof that civilization advances through shared knowledge. And perhaps that is the true legacy hidden inside every piece of steel surrounding us today. The story of iron is ultimately the story of humanity itself. It reminds us that the greatest discoveries are rarely made in a single moment. They are built, one insight at a time, by generations of curious people willing to keep learning from the world around them. Let's return to where this story began, a quiet landscape, a field scattered with reddish-brown stones. For thousands of years, people walked past them without a second glance. Nothing about those rocks suggested they would one day support cities, power industries, or connect continents. Yet hidden inside them was one of history's greatest opportunities. Iron did not transform civilization because it was rare. It transformed civilization because humanity learned to reveal what had been hidden all along. That journey took thousands of years. It began with mysterious fragments that fell from the sky. It continued through generations of failed experiments. Hotter furnaces were built, stronger fires were tested, patient blacksmiths refined their craft, step by step, without ever understanding the chemistry behind it. Slowly, those discoveries accumulated. Iron became steel, simple tools became engines, small workshops became factories. Eventually, the same element locked inside ordinary stone became the framework of the modern world. Perhaps that is the deepest lesson this story offers. History is rarely changed by a single dramatic discovery. More often, it changes because ordinary people keep asking questions, testing ideas, learning from failure, and passing knowledge to those who follow. Iron is more than a metal. It is a reminder that progress is built layer by layer, generation after generation. The next time you cross a steel bridge, ride a train, enter a skyscraper, or simply hold a piece of metal in your hand, remember that you are witnessing the result of a journey that began long before written history. A journey that started with an ordinary stone and helped reshape the human world. Sometimes the greatest revolutions are hidden inside the most ordinary things. Iron reminds us that knowledge, not rarity, is what unlocks the true value of the world around us, a lesson that remains just as powerful today as it was thousands of years ago.